All right, this time I want to do one where, again, it's a quadratic, but you're going to solve it like factoring. So you kind of need to view this as like, let me see if I have pen over here, like 6x squared minus 7x plus 2 equals 0. And so anytime you have a quadratic, you always bring everything over, set it to equal to 0, and then you try to factor, So you might try like 6x and x, and then you're like, okay, well, if I put the 2 over here, that's too big. 12 minus 1 doesn't work. If I put the 2 over here, that's what? 6 and 2, that's not going to work. And so 6 and x are out. So then maybe you try 3x and 2x. Then you're like, okay, I want to get a 7. So let's see. If I put my 2 here, I get 4x. And if I put a 1 here, I get 3x. And I need both of them to be negative to get a negative 7x, and then a negative times negative is positive. So that's awesome. So you kind of need to view that the same way. The good news is your alphas match, so your angles are the same. So these are the same input. This is a cosine squared function. That's cosine, but do you see how it looks like a trinomial? And in fact, it looks exactly like that guy. Except instead of x squared as a function and x as a function, you have cosine squared and cosine, but it's the same principle. So if I know how to factor this in algebra, I know how to factor it in trig. So I still have 3, but instead of x, I have cosine of x over 2. All right, and then I have minus 2, and then I have 2 cosine of my x over 2, and then what, minus 1 equals 0. And you can check, like if I multiply those, I would get 6 cosine squared of my input. Outside, inside would give me negative 7 cosine x over 2, and then the last is 2. So I feel good. So now notice, just like in algebra, you'd set each piece equal to 0. So I'm going to set this guy equal to 0. Bring my 2 over, this is just algebra, not a lot of trig going on here. And again, your goal is to isolate the chunk first, and then isolate the function. So I'm going to divide both sides by 3. All right, so now I have my function isolated. So now I choose to do the inverse function. That's, again, my decision. So inverse cosine, inverse cosine. So again, I'm not limited by any rules of, being at the cap and being up here. That doesn't imply, or doesn't apply here because I chose this. So I get x equals 2, and then cosine of that. So x over 2 equals the inverse cosine, of 2 over 3. Now again, that one's not on the unit circles, so I am going to use a calculator. And when I do that, it gives me, what did it give me? 0.8411, and again, that's radians. So I'm kind of, where would I be at? Kind of up, like if this is a radius, I'm not quite that far. So, somewhere in here, that angle maybe, because not quite a radius up, so 84% of a radius to be exact. So that's my angle. So again, there's an x and a y at that location, and I am focusing on the x because this is cosine. And again, be careful, this is x over 2 is approximately this. So I'm trying to find my other angle. So again, with cosine, it would reflect down here, and the x value would be the same. They're both going to be positive there. So again, I can find a coterminal angle. So if that's up 0.8411, this guy is down 0.8411. And so to find a coterminal angle, you can add 360 degrees or add 2 pi. So I'm going to add 2 pi. So again, 2 pi is what? 3.14 doubled is approximately 6.28. And again, I would just do this on my calculator. I just take 2 pi minus that and get an answer. So it's approximately 5.4421, and again, radians. And notice again, these angles, here we have this big giant angle, and then we have this one, no pattern whatsoever. So you need 2 formulas. Right, and so what we're going to add here is we know that we need 2k pi. Okay, and then the last step is, because this isn't really my angle, it's really half my angle, now I need to double everything. So I'm going to double that, and double that, and double that, double that, and double that, so that I get what x equals. All right, so I will come back to that math in a second. We're going to leave it there for a little bit. because we still have the other half. We haven't dealt with this half over here, and I'm going to go ahead and erase that stuff. Sorry about the noise. Okay, it doesn't want to erase that. I'm not sure why. Oh, there we go. It's just being picked, I guess. Okay, so to deal with this other part over here, same thing. I need to set this piece equal to 0. So I'm going to come over here. So I have what? 2 cosine x over 2 minus 1 equals 0. Again, my goal, first goal with any function is to isolate the chunk. Or the term would be a more mathematical word. Now I want to isolate the actual function. And then once you isolate the function, that is when you can choose to solve it using the inverse function. So I'm going to use inverse cosine to both sides. So again, I get x over 2 equal inverse cosine of 1/2. All right. So this is the deal. Again, I'm expecting 2. Now, the nice thing is that this guy is actually on the unit circle, and we've had, I don't know why all my examples have been cosine, but oh well, I guess we'll stick with it. So we'll have to do some in class where we're dealing with other angles, I guess, because all my examples are hitting the same thing. But again, this is that angle up here, and this is also half, that's negative square root of 3 over 2. This one down here. And so that's at what? Pi over 3 exactly, plus 2k pi, because again, there's no pattern there. And then this guy is what? A negative pi over 3, but you can't do that. So what is that? Is that 5 pi over 3 again? Yeah. And again, if you're not sure, you can count pi over 6, 2 pi over 6, 3 pi over 6, 4, 5, 6, 7, 8, 9, 10 pi over 6 and reduce it. And plus 2k to get pi. But again, we have the same issue on this one as we did on the other one, is this is not x, so we need to double everything and double everything so that the 2's cancel and I just get x, and then I get my 2 equations. So I actually get 4 equations, which should not be surprising because when we just have cosine, we tend to get 2 formulas. So if we have cosine squared, it makes sense that we should be expecting 4. All right, oh boy, sorry about that. Where did my thing disappear to? There we go. Okay, so now we just need to rewrite these nice, all right? So I'm just going to make a big X such that, and then, and you know, we can start with whichever one we want. Let's see. So here I'm going to get what? X is equal to, let's see, what is that? 2 pi over 3 plus what? 4k pi over there. And then the next one is what? 10 pi over 3 plus 4k pi. And again, I'm just doing the math that we didn't get done the other day, or the other day, a few minutes ago. And then over here, I'm going to do my approximations. So that ends up being what? 1.6822 plus, again, that's still going to be 4k pi. And this guy's approximation, 10.8842 plus 4k pi. And again, you know, I don't know. K is an element of the integers. So those are my answers. Now again, if they limit the domain, then you start, you know, subbing k equals 0 into these formulas and say, okay, which ones are inside my domain? So if my domain is, say, 0 to 2 pi, all right, well, if I sub in 0, all of these, let's see, this one's okay, 2 pi over 3. This one is 9 pi over 3 would be, what, 3 pi. So, you know, this one's, what, too big. I mean, it's like 3 1/3 pi. That's outside that already. If k equals 0 here, that's 1.6822 approximately. That's good. But again, if I sub 0 into here, this is 10.88 radians. And, you know, that's out. 2 pi is 3.14 times 2, that's 6.28, give or, you know, a little bit more radians, and this is way more than that. So even subbing in k equals 0, not all the formulas work, only 2. So if I limit my domain to that, then these are my 2 answers. But if I have no limits, then I end up with 4 formulas that could generate answers.